People tell me the Big Bang was an explosion, a massive, incomprehensible explosion, the greatest explosion in the history of everything, because it was the beginning of everything. That's what they show you in documentaries, a single point of light, then a dramatic burst outward into darkness, debris flying through empty space like a bomb going off in a vast, pre-existing void. That's what Hollywood gives you. That's what most science communicators settle for. And I understand why. It's a vivid image. It's dramatic. It fits into a mental model you already have. But here's what will shatter everything you think you know. The Big Bang was not an explosion. Not even close. And if you carry that explosion image in your head, you are misunderstanding almost everything that follows from it. Dark energy, the expansion of the universe, why the cosmic microwave background looks the way it does, why there's no center of the universe you could point to on a map. Every single one of those things makes no sense if you're picturing an explosion. Every single one of them clicks into place the moment you understand what actually happened. And I want to be upfront with you right now. At the very beginning, some of what I'm about to tell you, we know with extraordinary precision. Some of it, nobody knows. I will tell you which is which. That distinction matters more than anything else in science, and it gets lost almost every time someone tries to explain cosmology to a general audience. So stay with me for a while. Because what the Big Bang actually was, what it really means for space, for time, for the nature of reality itself, is so much stranger and so much more beautiful than a fireball in the dark. Let me explain what actually happened at the beginning of everything. Or at least, as close to the beginning as our physics can take us. Here's where the confusion starts, and I want to be precise about this, because the confusion is genuinely understandable. When you hear explosion, your brain does something reasonable. It reaches into your library of experiences. You've seen explosions. A firecracker. A demolition on the news. Maybe you've seen slow motion footage of a bomb going off. That elegant, terrible flower of fire expanding outward. And your brain files all of that under things that expand rapidly from a central point. So when someone says the universe began with a rapid expansion from an incredibly dense state, your brain says, oh, I've got a file for that. Explosion. And it passed in the image. The textbooks don't help. They use phrases like primordial fireball and the universe exploded into existence. Even serious cosmology texts sometimes say the early universe was hot and dense and expanded outward. The word outward is doing enormous damage in that sentence, and almost nobody flags it. Popular science documentaries show you an animation blackness, a single point. Then bang, matter spraying in all directions like shrapnel. Eventually cooling into galaxies and stars, the whole thing expanding through some pre-existing empty space like a shockwave moves through air. That image is wrong, not metaphorically wrong. Not simplified for clarity wrong. Physically, fundamentally wrong in a way that leads you to ask questions with no answers. Questions like, what was outside of the universe before the Big Bang? And where is the center of the explosion? And what did the universe explode into? These questions feel deep and mysterious. But they're not deep and mysterious in the way the questioner hopes. They're confused. They're based on a flawed mental model. They're like asking what's north of the North Pole. The question sounds meaningful, but the model that generated it was broken. People believe the explosion story because it maps onto everyday experience. We are creatures who live at human scales. We understand things moving through space. We understand cause and effect playing out in time. We understand one thing bumping into another. The actual physics of the Big Bang violates almost all of those intuitions, and that's genuinely hard to accept. It doesn't mean the physics is wrong. It means, as Richard Feynman would have told you with a grin, that nature doesn't care about our intuition. Nature does what it does. Our job is to follow the evidence and update our mental models however uncomfortable it gets. So let's build the correct model. Let's do this carefully, step by step, starting from something you already know and gradually pushing into territory that will feel genuinely strange. I promise that strange is better than false. I'll start with this. Forget the universe for a moment. Forget cosmology. Think about a rubber band. A simple, ordinary rubber band sitting on your desk. Now imagine that rubber band is covered in tiny dots, little ink marks, evenly distributed across its surface. Now stretch the rubber band. Pull both ends. Watch what happens to the dots. Every single dot moves away from every other dot. The dots near each other move apart a little. The dots far from each other move apart a lot. And here's the key observation, and I want you to really sit with this. No dot is the center. There's no special dot that everything is expanding away from. The expansion is happening in the rubber band itself. Every dot simply participates in the stretching of the medium it's embedded in. That's the universe. That's what's actually happening. Except instead of a one-dimensional rubber band, we're talking about three-dimensional space, or technically four-dimensional space-time, but let's hold that thought for a moment. The galaxies in our universe are like those dots. They're not flying through space away from some central explosion point. They're being carried apart by the expansion of space itself. The medium is stretching. Every galaxy recedes from every other galaxy. There is no center. There is no edge. There is no outside that the universe is expanding into. Space itself is what's growing. Now I need you to feel how different this is from an explosion. In an explosion, things move through space. A bomb goes off, and fragments travel outward through the existing space around them. The space doesn't change. The space is just a stage, and the fragments are actors moving across it. In cosmic expansion, there are no fragments moving through space. Space itself is the thing that's changing. The galaxies just sit there, more or less, while the space between them gets bigger. This is not a subtle distinction. This changes everything. Here's a thought experiment that Feynman would have loved. Imagine your ant living on the surface of a balloon. A two-dimensional ant living on a two-dimensional curved surface. Your entire universe is that balloon surface. Now, someone starts inflating the balloon. From your perspective, every other ant is moving away from you. The faster the inflation, the faster they recede. And the farther away another ant is, the faster it appears to move away, because there's more balloon surface expanding between you and a distant ant than between you and a nearby one. This is Hubble's law, the observation that Edwin Hubble made in 1929. Galaxies recede from us at speeds proportional to their distance. And now you can see why. It's not that distant galaxies are moving faster through space. It's that there's more expanding space between us and them. Now here's the crucial question for that ant on the balloon. Where did the expansion start? Where's the center of the balloon's surface? The ant looks around. Every direction looks the same. Every other ant is receding. There's no point on the balloon's surface that you could mark as the origin. The whole surface expanded. The center of the balloon, if you want to use that word, is not on the balloon at all. It's in a direction the ant can't access, a dimension the ant doesn't experience. Our situation in the universe is something like this. The Big Bang didn't happen at a point in space that we could locate on a cosmic map. It happened everywhere, simultaneously. All of space, however big space was at that moment, and we genuinely don't know. If it was infinite or very small and finite, was in that hot, dense state, and it expanded. All of it, everywhere at once. Let me be very clear about something, because this is where people get confused in a very specific way. When physicists say the early universe was small and dense, they are not saying the universe was a tiny ball sitting in empty space. They are saying that space itself was compressed. If the universe is infinite today, and it may well be, we don't know, then it was infinite at the moment of the Big Bang too, just infinitely more compressed. The observable universe, the part we can see, the sphere about 983 billion light years across, that contains all the galaxies our telescopes can reach. That region was indeed tiny, maybe the size of a marble or smaller. But that's the observable universe. A full universe, if it's infinite, was always infinite, just more densely packed with energy. I know that's hard to visualize. It's hard for me to visualize, and I've been thinking about it for years. But that's what the mathematics tells us, and the mathematics is backed by extraordinary observational evidence. Now let's talk about what we actually know happened, and when and how we know it. Because the evidence for the Big Bang is not a guess. It's not philosophy. It's some of the most precisely tested physics we have. In 1929, Edwin Hubble looked at distant galaxies and found they were receding from us. The farther away, the faster the recession. This meant the universe was expanding. And if you run that expansion backward in time, if you imagine reversing the movie, everything converges. Go back far enough and everything was in the same place at the same time, at enormous density and temperature. This is the basic logic that leads to the Big Bang. It's elegant and it's compelling, but by itself it's not proof. The real proof came in 1965. Two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to calibrate a microwave antenna. and kept finding a persistent noise coming from every direction in the sky, equally. They thought it was pigeon droppings on the antenna at first. Genuinely, they cleaned it out. The noise remained. It was coming from the universe itself. What they had accidentally discovered was the cosmic microwave background radiation, the afterglow of the early universe, the light left over from when the universe was roughly 318 years old and had cooled enough for atoms to form in light to travel freely for the first time. This afterglow is extraordinary evidence. It fills the entire sky. It's almost perfectly uniform, the same temperature, about 2.7 degrees above absolute zero in every direction. And the tiny variations in that temperature, the slight hot spots and cold spots that satellites like COBE and WMAP and Planck have mapped with incredible precision. Those variations match exactly what our models of the early universe predict, not approximately, precisely. The Big Bang Theory is not a guess about the distant past. It's a framework that makes specific, quantitative predictions, and those predictions have been tested and confirmed to extraordinary accuracy. Here's what actually happens in the very early universe, as best as we can reconstruct it. At around 1 second after the Big Bang, the universe is already 1 billion degrees. It's a sea of protons and neutrons and electrons and photons, all colliding frantically. In the first few minutes, protons and neutrons fuse to form helium nuclei, a process called Big Bang nucleosynthesis. The theory predicts that about 1% of ordinary matter should be helium. We look at the oldest, most pristine stars in the universe. We find about 1.5% helium. This is a direct fingerprint of the Big Bang, preserved in the chemistry of ancient stars. At about 318 years, the universe is cooled enough to roughly 3,000 degrees for electrons to combine with protons and form neutral hydrogen atoms. Before this moment, the universe was opaque. Light couldn't travel freely because it kept scattering off free electrons, like sunlight diffusing through fog. When atoms form, the fog clears. Light can travel. That light is what Penzias and Wilson detected. The universe literally became transparent. And the light from that moment has been traveling ever since, stretching as space expanded, cooling from 3,000 degrees to the 2.7 degrees we measure today. The stretching of light as space expands, that's called redshift, and it's another piece of the story. When space expands, the wavelengths of light traveling through it get stretched too. This is why distant galaxies look red. Their light has been stretched toward the end of the spectrum. This is not a Doppler effect in the traditional sense, not light shifting, because a source is moving away from you like a train whistle. It's space itself, stretching the wavelength of light in transit. It's subtle, but the distinction matters. Now, here's where I have to be honest with you in a way that most popular accounts aren't. All of that, the nucleosynthesis, the cosmic microwave background, the expansion, Hubble's law, all of that is extremely well confirmed. We are on solid ground up to fractions of a second after the Big Bang. But when people ask what happened at the exact moment of the Big Bang, at t=0, that's where we run into a wall, literally. Our equations break down. General relativity, which describes gravity and the structure of space-time, and quantum mechanics, which describes the behavior of matter at small scales. These two theories are our best physics. And they give us nonsense answers at the singularity at the very beginning. Infinities appear in the equations. Infinities in physics are almost always a sign that your theory is being pushed beyond its domain of applicability. Nobody knows what happened at t=0. That's okay. It's not a failure. It's an honest acknowledgement of the frontier. There's something called cosmic inflation that was proposed by Alan Guth in 1980, and it's worth talking about because it's become central to modern cosmology, and it also comes with enormous uncertainty attached. Inflation proposes that in an incredibly tiny fraction of a second after the Big Bang, from roughly 10 to the minus 26 seconds to 10 to the minus 32 seconds, the universe underwent a period of exponentially rapid expansion, growing by a factor of at least 10 to the 26th power. This is much faster than the ordinary expansion that has continued since. Why do physicists take this seriously? Because inflation solves several puzzling features of the universe we observe. The universe looks the same in all directions to extraordinary precision, but regions on opposite sides of the observable universe are so far apart that light could never have traveled between them in the time since the Big Bang. How are they at the same temperature? Inflation answers, they were once in causal contact in the tiny patch before inflation began, and then inflation stretched that patch to cosmic scales. Inflation also predicts a specific pattern of temperature fluctuations in the cosmic microwave background, and observations match those predictions well. But here's what I need you to hear. Inflation is not confirmed. It is a compelling theoretical framework with observational support, but the specific mechanism, what drove inflation, what ended it, is unknown. There are dozens of different inflationary models, and distinguishing between them requires observations we haven't yet made. Some physicists are skeptical of inflation entirely. This is an active, contested area of research, and anyone who tells you inflation is as solid as nucleosynthesis is misrepresenting the state of the field. And then there's the question that really cuts to the bone: what came before the Big Bang? And here I have to tell you something that feels like a dodge, but is actually profound. The question may not be meaningful. Time, as we understand it from general relativity, is part of the universe. It's not a backdrop that the universe sits inside of. Space-time is a structure, and that structure came into being with the Big Bang. Or, at the very least, our concept of before breaks down at or near the singularity. Asking what came before the Big Bang may be like asking what's south of the South Pole. The question uses a concept, before, that doesn't apply in the regime. We're asking about Stephen Hawking and James Hartle proposed a model in the 1980s in which time near the Big Bang becomes like a spatial dimension, such that asking what came before is exactly like asking what's north of the North Pole. There's simply no answer because the question assumes a geometry that doesn't exist there. This is a beautiful idea. It's also speculative. We don't know if it's true. Roger Penrose has proposed something called conformal cyclic cosmology. The idea that our Big Bang is one in an infinite series, that universes are born from the endpoint of previous universes in a great cosmic cycle. Lee Smolin has proposed that universes give birth to new universes through black holes. String theorists talk about a landscape of possible universes and eternal inflation spawning bubble universes endlessly. These are serious ideas from serious physicists. They are also untested and, in some cases, possibly untestable. I'm telling you about them because they're intellectually exciting and because they represent genuine attempts to push physics into territory where our current tools fail. But I won't pretend they're established science. They're not. What I find truly extraordinary is what all of this implies about our relationship to reality. Think about what the expansion of the universe actually means. There are galaxies out there so far away that the space between us and them is expanding faster than the speed of light, not because anything is moving faster than light through space, which is forbidden, but because there's enough space expanding between us that the cumulative effect exceeds light speed. Light from those galaxies will never reach us. They are beyond our cosmic horizon, forever inaccessible. Our observable universe is a bubble within a larger universe that we can never see. Not because we lack the technology, but because the universe's geometry forbids it. We are, in the most literal sense, cosmically isolated from most of existence, and the expansion is accelerating. In 1998, to teams of astronomers measuring distant supernovae, standard candles whose brightness tells us how far away they are, discovered that the universe's expansion is not slowing down as gravity should make it. It's speeding up. Something is pushing space apart, accelerating the expansion. We call it dark energy. It makes up roughly 68% of the energy content of the universe. We have no idea what it is. The simplest model, a constant energy density of empty space, called the cosmological constant, fits the data but has a severe theoretical problem. Quantum mechanics predicts the energy of empty space should be about 10 to the 120 times larger than we observe. That's a 1 followed by 120 zeros. The discrepancy between theory and observation is the largest in the history of physics. Something is catastrophically wrong with our understanding, and we don't know what. This is the situation we're actually in. We have a universe that began not with an explosion through empty space, but with the expansion of space itself from an extraordinarily hot, dense state about 6.8 billion years ago. We can test this back to fractions of a second. After that, beginning with extraordinary precision, we have fossils of that early state, the cosmic microwave background, the abundance of helium and hydrogen, that confirm the broad picture beyond reasonable doubt. And then, Staring at the universe today, we find that 95% of its energy content, dark matter and dark energy, is completely unknown to us. We have a theory of the beginning that works beautifully in a present-day universe that is mostly mysterious. What should you take from all of this? Not the explosion, never the explosion again. When you think of the Big Bang, think of space itself expanding, every point moving away from every other point. No center, no edge, no pre-existing void it's expanding into. Think of the cosmic microwave background as the actual light from that ancient hot plasma, detectable today, proof that the universe was once unimaginably different. Think of the Big Bang not as the beginning of stuff, but as the beginning of the conditions we can describe with physics and honest uncertainty about what, if anything, came before. Think of yourself as standing in the middle of a reality that is mostly dark, mostly unknown, expanding toward a future that will eventually leave our galaxy alone in an empty, cold, dark cosmos as all other galaxies recede beyond our horizon and the last stars burn out. This is what the evidence says. It's not comfortable. It's not the explosion in the dark that makes us feel like we understand, but it's real, or as close to real as we can currently reach. Here's what Feynman understood that I think gets lost. The goal is not to have a satisfying mental image. The goal is to not fool yourself. And the most common way people fool themselves in cosmology is by keeping the explosion analogy long past the point where it's doing any useful work. Let it go. Hold the strangeness instead. Hold the fact that space expands. That time had a beginning in any meaningful sense we can access. That the universe is 13.8 billion years old, and we can prove it, that most of it is invisible to us and always will be. We are, as Carl Sagan said, a way for the cosmos to know itself. A universe that began as a hot, dense, uniformly expanding medium somehow produced, after 13.8 billion years of expansion and cooling and gravitational collapse, and stellar nucleosynthesis, and planetary formation and chemistry and biology, creatures who can ask what it all means. We can't fully answer that question, but we can be rigorous about what we do know, honest about what we don't, and permanently joyfully astonished that we get to ask at all. The Big Bang wasn't an explosion. It was something far stranger, far more interesting, and far more true. And we're only just beginning to understand it.